We're going to start with a topic called complex numbers. Complex numbers are a lovely part of mathematics, interesting part of mathematics. In fact, there was an Irish mathematician, Rowan Hamilton, who was centrally involved in the use of complex numbers. And believe it or not, I would be very surprised if you didn't use complex numbers at some stage today on your mobile phone to work and show some pictures or look at some pictures or images on your mobile phone. And I'll explain how complex numbers comes into that in a moment. But a hugely useful part of mathematics. You couldn't have computer games without them. You couldn't have so many things on our screens without them. And really, really helpful when it comes to mathematics. But let's go through complex numbers. So this is a guided tour. In the way the notes are done, and hopefully you have the notes there, and you can use them, I start each subsection with a little banner page. And that really allows you to say, look, I know that bit, I can move on to the next one, I can move on to the next one. Or at some stages say, I don't know that, I better go back and check and do a question or two in that space. Because the way I understand it is that you know enough of the maths already, and we're just here to fill in gaps where they exist. There might be a bit that you didn't pick up at the time when it was explained, or maybe you were sick or whatever. And we just want to fill in those gaps, because sometimes those gaps are important because they might block you from doing a question. But there's no bit of the maths course that's harder than any other bit, just a bit that you haven't sort of filled in the gap for. So let's start with complex numbers. Complex numbers are numbers that are in two parts. They have a real part and an imaginary part, or a real coefficient and an imaginary part afterwards. So this is the number z equals 5 plus 12i. It's got a 5 there and a 12i. I is an imaginary number, and it's given by definition as the square root of minus 1. So if you were to square I, you'd get minus 1. So that's the definition of it. And C is the set of complex numbers, which is given as a plus bi, where a and b are real numbers, and I is this imaginary square root of 1. It's drawn on an Argonne diagram, very much like your XY diagram. There are two dimensions, so why not make them perpendicular? So this is the imaginary axis, and this is the real axis. The real is considered the x-axis, this is the y, or this is the real number line. So for example, the complex number 3 plus 4i is seen as 3 out and 4 up. We don't write it as 3, 4, but it's very similar to it. We write it as 3 plus 4i. So it's 3 of those and 4 of those, like 3 apples and 4 oranges. 7 plus I is out here, and 12 plus 5i is out there. But it's the full coordinate. It's the 4 quadrants, just like your Cartesian system, your xy. And you can have minus 1 minus I, minus 2 plus 5i, or 4 minus I. So it can be any one of those quadrants. And if two numbers are the same, if I want to get to, say, 4 plus 2i, the only way I can get to it is to have 4 apples and 2 oranges. I can't make any other combination. I can't compensate apples for oranges. So if a plus bi is the same as c plus di, the two real parts must be the same and the two imaginary parts must be the same. But we'll deal with that later. The Argonne diagram can also be shown as the distance from 0, 0. So for example, the length of this number, 12 plus 5i, is further away from 0 plus 0i than 7 plus 1i. You can see if you were to walk from here to here, that's a further walk. Okay, so you can see the Argonne diagram like this. In fact, when you think about it, if you go back to a thing called the number line was really quite boring. Here you've got 0, you've got the number 1, the number 2, the number 3, and you can keep on going in that direction. Or for a bit of excitement, you can go minus 1, minus 2, minus 3. But there's really not a lot else you can do. Okay, you might meet the number pi along the way at 3.14, or the number e or something. But really it's just, or half or something that might be nice, or the square root of 2 might be here. But they're just the number line. That's all they are. and you never move onto this space or this space. So you're really constrained by this narrow tunnel or chain. Whereas with complex numbers, what happens here is you can imagine a number out here, or here, or here. So the numbers are all over the page. Now they can also be on this line. They're complex numbers as well, but these are complex numbers that are not on the ordinary real number line. So this is 1, 2, 3, 4, 5, so that's 5 plus I, and this is 4 plus 3i. The distance of a complex number from 0, 0 is an idea of its length, if modulus they call it. But we can get it by saying that's 7 plus I or 12 plus 5i. So now let's look at some definitions. Complex numbers is not a difficult part of your course. It's generally relatively straightforward, but it comes with its own symbols. So it's like new letters of the alphabet. So if you didn't learn the letter T, you know, going through primary school, you'd know all the other letters, but you could never have a cat. You'd have to have a dog instead, you know, or live in a house rather than a flat. So with these numbers and these symbols, it's important to remember and recognize them for what they are. So the first one of these is this fella here, the absolute values. Two lines perpendicular, opposite, around either a variable or an expression. And it says this is the length of. And the length of a complex number is given by this formula here. So for the general complex number a plus bi, the modulus, or the FOD, is given by the absolute value, because the distance can be minus or plus. But if you've got to go minus 3 kilometers somewhere, it's still 3 kilometers in length, maybe in a minus direction. So that's why we have the modulus there. And the definition of a modulus is bars around a plus bi, bars around the complex number, and z bar is equal to the square root of a squared plus b squared. So you take the coefficient of the real one and the coefficient of the imaginary, and you square both, and then take the square root. So here's the first question. Calculate the modulus or absolute value of 3 plus I. So what you do is you put bars around it. Then you take the square roots of 3 squared plus 1 squared. 3 squared is 9, 1 is 1, 9 plus 1 is 10, and you get the square root of 10. So here it is in the diagram. We've got 3 out and 1 up, so 3 plus I, 3 squared and 1 squared. Note it's not minus the 1 squared. Distance is always out there. So if that was a right angle triangle, because these are perpendicular, just like the xy coordinates, we've got 3 squared plus 1 squared is root is 10, or getting the square root of that. So we're using the Pythagoras theorem. The square of the other two sides is equal to the square on the hypotenuse, the side opposite the 90 degree. So that's our modulus length. Now the question now is asked, is this number here bigger than this number here, or is the length of this number here bigger than the length of this? The question is it further from 0, 0, 0 plus 0 I? So let's take the 7 plus I. Well, the 7 would be 7, that'll be 1, so the square root of this will be 7 squared plus 1 squared. Whereas in this case, this is 12 and 5, so that would be 12 squared plus 5 squared. And 12 squared plus 5 squared is the square root of 169, or 13. And that's the square root of 50, and the square root of 50 is just a little bit over 7. So 13 is more than 7 and a bit, so therefore the modulus of z, the modulus of z2 is greater than the modulus of z1, and that's it. Now, another way of representing complex numbers is take the number 4 plus 3i, and they say 4 plus 3i is out there. We can say 4 and 3i, or we can say if you go in this way for this length of time, so that's 4 squared plus 3 squared, or 5, by this angle here. Now, how do you find that angle? Well, when I'm ever looking at an angle in a right angle triangle, first thing I always say is draw an arrow. And the arrow should bring you to the opposite of that angle. Because that's a right angle triangle, this should tell you that that's the hypotenuse because it's opposite the 90 degree. And if that's opposite, that's hypotenuse, this must be adjacent. If you're doing this course as Gaeilge, that would be the Orcorach, Goni, and Rudata Oscor. Then you've got the Conjugate, and you've got the Theorem. So what we have now are the definitions of those three things. We know that's a 5, we know that's a 3, and that's a 4. If we take the tan of this angle here, we get opposite over adjacent, or Orcorach over Conjugate. So we get the tan of that is 3 over 4. The sine is Orcorach or Theorem, so we've got opposite over hypotenuse, 3 over 5, and the cosine is adjacent over the hypotenuse. So how might we write that? We might say that u is 4 plus 3i, or 4 over 5 plus 3 over 5 times I times 5. 5 times 4 over 5 plus 3 over 5. But what's 4 over 5? 4 over 5 is adjacent over hypotenuse, or cosine theta. And 3 over 5 is opposite over hypotenuse, or Orcorach or Theorem, and we've got sine theta. So what we have is a nice way of writing complex numbers where u is equal to 5, which is really the modulus of u, the length, how far it is, cos theta plus I sine theta, with the brackets around both. So we have a number of ways now of representing complex numbers. And we'll find this one really, really useful when we're talking about other theorems later, the Myverse theorem and calculating roots and square roots and stuff. So there's our polar representation. We say 5 cos theta plus I sine theta. That's our variable there. U plus 4 plus 3i. The imaginary, the real, and that's the polar representation. In general, if we had A and B, A plus BI, and this was or Z, we would find that this was A squared plus B squared in length. And tan of theta, if we again take the theta out, this is the opposite, and this is the adjacent. So Orcorach and Conjugate, and this must be the hypotenuse because it's opposite the 90. And again, we'll find that if we draw that up, we can say we want it in this form here, but that B over that would be sine, and A over that would be cos. So if we wanted this times A over the square root of A squared plus B squared, plus B over A squared plus B squared I, we should be able to generally get the formula, well, that's cos theta and that's sine theta. So the general form of a polar representation is that, or cos theta plus I sine theta. And we used or there just because it's handy. Very often we think of it as a radius, and we could imagine it being a circle because depending on the angle, so or would be the middle of the circle. So the or would be the radius from the middle out to the imline or the perimeter. So that's that. So take a breather for a moment. We now say, can we identify what a complex number is? Can we put one on an Argonne diagram? Can we calculate cosine and sine from a triangle? And can we use them in the exam? So that's the first thing that they will ask you to do. And we'll do some questions like that later. The next task that they give you with complex numbers is addition, subtraction, and multiplication. So the addition is something that you did way back in primary school, so addition isn't difficult, but there's two parts. You've got a real and an imaginary, and a real and an imaginary part. So here we're asking for 1 plus 3i and 4 plus 2i. So it's like, you can consider this in many ways like apples and oranges. Una has 1 apple and 3 oranges, and Vincent has 4 apples and 2 oranges. How many have they got between them? Well, you'd add the apples together and you'd add the oranges together. So here we write it out. U plus V is 1 plus 3i and 4 plus 2i. But we link the two real parts together, and we've got 1 and 4, and we link the two imaginary parts together, the 3 and the 2. So 1 plus 4 gives us 5, and 3 plus 2 gives us 5. And that's how we do it. This is what they would look like on the Argonne diagram. 1 plus 3i is here, 4 plus 2i is here, and 5 plus 5i is here. So if we add this to this, we get that. So it'd be like going out 1 step east and 3 north, followed by 4 steps east and 2 north. We'd end up with 1 and 4, or 5 steps east, and 3 and 2, 5 steps north. And that's how it would work. The order doesn't matter. We can say u plus v and add them together, or v plus u. We'll all end up at 5 plus 5i. So that's how that works. Addition is commutative. The next step that we do, like in primary school, was subtraction. And here we're going to subtract one thing from another. So we've got 5 plus 5i and 1 plus 3i. Again, this could be 5 apples and 5 oranges, and somebody wants to borrow or take 1 apple and 3 oranges. And you just take them one from each other. So z1 minus z2 is 5 plus 5i minus into 1 plus 3i. So 5 plus 5i multiplying in is minus 1 minus 3i. Taking the reals together, 5 minus 1 gives us 4, and taking the imaginary 5 and minus 3 gives us 2. And that's how we do that, and that's subtraction. So here we've got 5 plus 5i out here, and if we subtract 1 plus 3i from it, we'll take away 1, we'll take away 3i, and we end up here. And if we subtract 4 plus 2i from that, the 2i brings us down, and the 4 brings us across. And again, it's just, subtracting. We can subtract, or we could have started going back this way or whatever. Now, so far all that's happened is we've just added numbers and taken them apart like east and west. But now we're going to multiply two complex numbers by each other. 1 plus I by 3 plus I. Now, we'll start by multiplying the first number into those. So 1 into 3 plus I into 3 plus I. So 1 by 3 is 3. That's the first. Then the outside, 1 by I. Then the inside, 3i. And then the last, I squared. So we have 3 plus I plus 3i plus I squared. Now remember that I squared is defined as minus 1, because I was defined as the square root of minus 1. So we're going to change that I squared. So the 3 plus I plus 3i we keep, and the I squared becomes minus 1. So now we have the answer, but we have it in several parts. So we've got the real number 3 and the real number minus 1. So 3 minus 1 is 2. And in terms of imaginaries, we've got I and 3i, we've got 2 plus 4i, and that's the answer. So what we've done is we've taken this number here, 1 plus I, 2 plus 4i, or sorry, 1 plus I, and 3 plus I, this one here. We've multiplied this by this and ended up here. So it's surprising really if this number multiplied by this number gives us this number here. So Z1, Z2, Z3. So we've learned how to multiply. Nothing particular, it just ends up as another complex number. We don't have to notice too much yet, but later on we might. We might notice, for example, that that angle there, theta 1, and this angle here, theta 2, and this angle here, theta 3, are in some way related. But first of all, we know how to do the multiplication. So there's the multiplication in a sort of slightly more polar form. We can see there's the 1 plus I, the 3 plus I, and the resulting answer there, 2 plus 4I. That's near enough, 2 naught naught. This is further out, and this seems to be further out again. Now, take a breather again. We're now on another topic. The subtopic here is complex conjugates and division. So they can also ask you to do division of complex numbers or to use things called complex conjugates. So again, if this is the area, you go to this part of the screen and you roll the video onto that part if you want to return or whatever, or skip it if you already know it. Where a complex number is denoted by z equals a plus bi, and they all are, z bar is bar a plus bi. So again, what's happening here is a new letter of the alphabet, or a new symbol, is being introduced. This time the symbol is on top. It's a flat line above the variable, or above an expression. And it's defined as the same real part and a different, the opposite, imaginary component. And there's something special about them. They go in pairs and they're twins, these complex conjugates. And what's really interesting about them is when you add complex conjugates to each other, they end up with a real number. Or when you multiply them by each other, they give a real number. So they're sort of magic in that no matter what you do with them, if you've got two of them, they go as pairs, they sort of follow each other around. And when you add them together, real number, multiply them together, real number. So let's look at it for a moment and see what they are. Here's an example of a complex number, 3 plus 4i. It's 3 out and 4 up. But its complex conjugate is 3 minus 4i. So if this was z1, this would be called z1 bar. It would have that bar on the top. So this is the twin of that. In fact, if you look at it, imagine that was a mirror and you were looking into the mirror. This would be the reflection. Now, it doesn't have to be, I mean, this distance here is 4 and this distance here is 4. And they're both the same distance across, 3 across. Now this, we could have called this one U1. And then this would have been U1 bar. The bar doesn't have to be on the bottom. It can be anywhere. Once you pick a complex number, the twin is the one in the mirror opposite it. For example, in this case here, if this was Z2, the number minus 1 minus I, Z2 bar is its mirror image on the other side. Okay? So that's the process of a complex conjugate. They're just a twin out there. So let's add two of these together. Let's add 1 plus 2i and 1 minus 2i, because they are the twins of each other. So this is u bar and this is u. 1 and 1 gives 2. 2 and 2i and minus 2i gives naught I. So the answer is there. So u and u bar turns out to be there. In a way, you could say this is go out east and 2 north, and then go out east and 2 south, or minus 2 north, and you end up there. You end up on the number line, the ordinary, the one that you're familiar with, the standard number line that is just what we would often call the x-axis, the horizontal line. So now let's look at multiplication for a moment and see if it works for multiplication. Here we've got the number 1 plus 2i and the complex number 1 minus 2i. So 1 plus 2i by 1 minus 2i, we have to do the multiplication for it. So it's 1 plus 2i by 1 minus 2i. And the answer turns out to be 5 plus naught I. Let's see how we got that. 1 plus 2i by 1 minus 2i. Get the FOIL method. 1 by 1 is 1. 1 by minus 2i is minus 2i. 2i by 1 is 2i. And 2 by 2 is 4. I by I is I squared, and the minus is there. The 2i and the minus 2i cancel. So we end up with 1 minus 4i squared. I squared is minus 1. So 1 minus 4 times minus 1, which is 1 plus 4, which is 5, plus 0i. 5 plus 0i. So we multiply this by this, we end up here. We now turn to division. Division is a two-step process because it's very difficult, or we don't know the way of dividing by 2 plus 3i. So it's tricky to do. So what we do is we involve a midpoint, like a trick or a cheat in a way, and we say, let's put something in here for the moment so that we can actually, solve this question. So what we do is we look at 1 plus 8i over 2 plus 3i, and we're going to multiply above and below the line by the same number. So for example, if I multiply above the line by 3 and 3, I don't change it, 7 and 7, 10, 10, 10i, 10i, doesn't matter. But I'm going to choose a particular number to multiply by. I'm going to choose the twin, the complex conjugate of this one on the bottom, right? So it's the 2 minus 3i. Complex co-Conjugate. So I'm looking at the twin here of that by 2 minus 3i. So I'm going to multiply above and below by the same number, but it's the twin of the one on the bottom. So effectively what I've got is, on the top now, I've got 1 plus 8i times 2 minus 3i. And on the bottom, 2 plus 3i by 2 minus 3i. So 1 plus 8i by 2 minus 3i. And on the bottom, 2 plus 3i by 2 minus 3i. So pick your favorite, either do A or B, and just take a minute to do those calculations. So just multiply those out. Okay, so using the FOIL method, 1 by 2 is 2, 1 by minus 3i is minus 3i, 8i by 2 is 16i, 8 by 3 is 24, I by I is I squared, and there's a minus 3 there. So that turns out to be 2 minus 3i plus 16i, and I squared is minus 1. So minus 1 by minus is a plus, so that becomes 24. And if I join the real numbers together, I have 2 and 24, that gives me 26. And if I join the imaginary numbers, 16 and minus 3, I get 13i. Now, you may have done B instead. So 2 by 2 is 4. 2 by 3 minus 3i is minus 6i. 2 by 3i is 6i. 3 by 3 is 9. I by I squared. Minus by plus, minus. 4 minus 6i plus 6i. And the I squared is minus 1. So minus 1 by minus 9 is plus 9. Adding them up together now, the reals are 4 and 9, that's 13. And as I expected, the i's cancel because I chose that number specifically so that I wouldn't have imaginary parts on the bottom. So it's important that that came out without any I parts. So now, that's what was going on here in these pages. I expanded out the various expressions. I multiplied them all out, and I got 26 plus 13i over 13. 13 into 26 is 2, and 13 into 13i is I. So effectively what that's saying is that if I take this number 1 plus 8i and divide it by this number here, I end up here. So that's division. Now we know how to add, subtract, multiply, and divide complex numbers, and to use the complex conjugate, and to put them on the Argonne diagram and use the polar coordinates. But let's look at an observation as well that's of note. Rather than just looking at complex numbers and saying this by this gives you this, or this number here divided by this number here gives you this number here, they started looking at them and saying, is there a pattern between Z3 when Z3 is Z1 by Z2? Or is there a pattern? So what they found was that when they multiplied two complex numbers by each other, the angle of the answer was the addition of the other two angles. So in other words, when you multiplied, you added the angles they made with the x-axis. And they also found that when dividing complex numbers, the angle of the Z1 over Z2, the resulting answer when you divided one by the other, was subtracting the angles. They further pointed out that when they multiplied two complex numbers by each other to get Z3 from Z1 and Z2, that the distance Z3 was from 0 was the product of the other two distances. So for example, if this was 2 away and that was 3 away, this would be 6 away. And likewise, when they started dividing numbers, and they said if you divide Z1 by Z2 to give Z3, that the distance Z3 away is the distance Z1 is away divided by Z2. So for example, if this is 8 and this is 4, this is 2 in terms of length. So let's look at how that looks on a picture. Let's go back to the multiplication we did, 3 plus I by 1 plus 2i. If you multiply this number by this number, you end up here. What we're finding is that the first angle was this, the first number, the second angle was this, and the third angle was the addition of the two of them. So if you multiply this by this, you rotate. What they found was multiplication causes you to rotate. So instead of just multiplying out on the number line, getting bigger or smaller, you are rotating. And they also found that when you divided this number here by this number here, you ended up with this number here. And that this angle here, theta 1, let's say, when you took away theta 2, you ended up with theta 3, but that was, theta 3 was theta 1 minus theta 2. This angle here is the same as that angle there. So you can see there that division caused you to rotate. Division, actually, you rotated clockwise, whereas multiplication, you rotated anti-clockwise. And the bigger the number was, the further the answer went away from 0. If it was just 1, it would have stayed the same distance away. And in fact, that's a very useful thing to know. So for example, if you've got the complex number 1 here, let's say the complex number 1 plus 0i, that's 1 plus 0i. And let's say I multiplied that by the number I, or I is really 0 plus I because there's no real part. But let's say I multiply it by I times 1 is I, and I times nothing is nothing. So if I multiply that by I end up with 0 plus I. I end up here. If I multiply I by I get I squared, and I squared is minus 1. But there's no I in it. And if I multiply that by I get minus I. What I'm showing here is that if you multiply by just the I, you end up going round in a circle. You don't get any bigger, you just keep on going in that direction. And if anybody here was using a mobile phone today, you probably have often seen pictures on your mobile phone. I won't show you pictures now. But if you turn them so they go landscape and portrait, you'll see that what happens is that the image changes. So in order for that to work on your phone, you've got to be able to multiply by the imaginary number I. If you wanted to multiply by something less than I or less than 1 in size, the multiplication would end up like this. And you'd end up getting increasingly smaller circles. And if you're multiplying by larger than 1, you'd start going out. So if anybody has ever played a computer game, the way back the old computer games, where somebody would get bigger if they ate something or whatever, all that was going on, or rotating or rolling, all that was happening was multiplying the person by a complex number. So if you're looking at a two-dimensional game or a three-dimensional game, you can be sure in the background that complex numbers are what's managing that all the time. So we couldn't live our lives without complex numbers, and thankfully it was an Irish mathematician as well, Rowan Hamilton, who got into this and noticed this and was very excited by what he had spotted way back before computers were invented. He was so excited on a walk in Dublin that he scratched his thoughts into a bridge along the canal so he wouldn't forget them. And people go every year to Broom's Bridge to actually celebrate his achievement at the time. But that's what we know now about complex numbers, and that's how our computer games or our mobile phones are used all the time. Now, we'll turn now to a lovely observation about complex numbers, and we're using the polar bit for this. So it's called de Moivre, after I suppose Mr. de Moivre, I presume, and various theorems, and how to find roots. Before we do that, let's just explain what might be going on. If we have the number 1 here, and I, and minus 1, and minus I, we can see that if we go across here, that the square root of 1 we would have normally called as 1 and minus 1. So there are two pictures of those. Square root of 1, you have two numbers. The square root of 1 is plus or minus 1. So here or here. But the fourth root of 1 is actually the square root. It's plus or minus the square root of 1. Well, it's what could make it a 1? Well, I minus 1 squared would also be a root of 1, a fourth root. Let me explain that again. Sorry about that. What I want is a number that when multiplied by itself 4 times gives you 1. Well, we know that the number 1 multiplied by itself twice is okay. We know that minus 1 by minus 1 brings you back. What we're finding here, if we take this number I and we say one of them, 2 of those, 3 of those, and 4 of those brings you back, I must be a fourth root. If we took minus I, we say one of those, which is 3 long, plus another one which would be 3 long, plus another one which would be 3 long, plus another one would bring you back. So basically, we can keep on going around circles here and saying, how do we find the roots of something? So if somebody said, what is the cubic root of 1? I don't know. But we know that that's 1. And what I want is the circle one, but instead of dividing it into 2s or 4s, I'm going to divide it into 3s. So I'm going to divide it into third here. Sorry, that should be there instead. I'll just draw that again so it's a bit clearer. So that looks like the circle is split in 3. I have 120 degrees here, another 120 here, and another 120 here. Or if you like to do it as 2 pi over 3, 2 pi over 3, 2 pi over 3. This angle here would be 60. And I could find out what that length is there. Actually, it's whatever. It's 1 minus 1 plus root 3 over 2i minus 1 minus root 3 over 2i. I can get that from, like, if I take a 60-degree angle there, and if I know that that's 1, I can work out that this must be root 3 over, sorry, that's a half, yeah. So root 3 over 2, sorry, that's what that should be. Half squared plus that squared should give me that. I can work out what the cosine is, or whatever way I want. If we look at it there, opposite to 60 is this side here, so this must be opposite. This must be the hypotenuse. So tan of 60 is root 3 over 2. I can look that up. So that's basically what we're finding there, is that minus 1 plus or minus root 3 over 2 is a complex number. And we'll show later that if we actually cube that, we'll end up 1, 2, 3. It'll be a root of 1. So let's start de Moivre's theorem. De Moivre's theorem says that every complex number can be written as or cos theta plus I sine theta. We did that earlier in the definition of a complex number. We said that this number here, or that being theta, this must be or cos theta, because or cos theta over or is just cos theta, and cos theta is the adjacent over the hypotenuse. And this must be or sine theta, because that over that is the vertical part, or the imaginary part. So or cos theta plus I sine theta, if we keep the or on the outside, is the complex number. So that's the complex number. Now, if we decide that we want to multiply the complex number by itself, if I've got a complex number and I decide to multiply it by itself, what am I doing? If I'm multiplying, I'm rotating. So if I take this number here, Z1, and I want to get Z1 squared, I just get Z1 by Z1. And that means I must take this angle and go again, take this length and go again. Now, if I wanted to get the square root, I would take this angle and halve it. I would take this length and get the square root of it. So it might just be that length. So the nth power of the complex number, if I want to get z to the n, I get all of this to the power of n. But or to the n, I can just bring that back here and just leave this bit to the power of n. And what de Moivre found out was that cos theta plus I sine theta to the power of n is you could take the n down and slip it in here and say that's the same as cos n theta plus I sine n theta. And that was very powerful observation. And you might remember that you did something like cos theta plus I sine theta. if we wanted that squared, we could say that that's equal to cos 2 theta plus I sine 2 theta. If we did this the old way of FOIL and method, we'd get cos theta plus I sine theta by cos theta plus I sine theta. And if we just took the real parts for the moment, that would be a real part. Cos by cos would give us cos squared theta. I by I would be minus. Sine by sine would be sine theta. What we would find is that the real part, that cos theta, was given as cos squared theta minus sine squared theta. And that's where all of these formulae that we have on the trigonometry section came about. But that's the Myverse theorem, and we're going to hold on to that. We might keep that as a note, highlight it, and say we're going to be able to need that. Don't know if that's in the, can't remember if that's in the log tables, but remember that that's part of your tool. Note that for every complex number, if z is equal to r cos theta plus I sine theta, you don't have to go with just the theta. You can say theta plus 2 pi. Theta plus 2 pi. So for example, the two square roots can be written as follows. So if I have the number 1 here, 1 plus naught I could say that's the complex number z is equal to 1 plus naught I. Or I could say the length is 1. Cos theta, cos naught, I'd say, plus sine naught, I sine naught. But the angle naught is also the same as the angle 2 pi. So really I'm saying that it's cos 2 pi plus I sine 2 pi, or cos 4 pi plus I sine 4 pi, or cos n, 2 pi n, or 2n pi, I sine 2n pi, or 2 pi n, whatever way you want to do it. So that's what we can do. And then the square roots can be written as follows. The square root of a complex number is you take the square root of its modulus. So if the original was 25 away from 0 plus 0i, the square root will be only 5 away, because the square root of 25 is 5. So it's the square root of that by cos plus, and here I'm dividing by the 2. So in the first case I'm using 2 pi, then I use 2 times 2. So for example here, I'm going to take the cos 2 pi, then the 4 pi, then the... So if I wanted to get the two roots of that, I would say it's cos 2 pi over 2 plus sine 2 pi over 2, or it's cos 4 pi over 2 plus I sine 4 pi over 2. And 2 pi over 2 is actually just pi, and that gives me a different answer because cos of pi, I think, is a different number. Okay, then cos of pi, I think, is minus 1. So that's how we do that. So to get the square roots of that, if I wanted the nth roots, I'd say instead of r, it's 1 over r to the n, and then each of these I divide by n. So if I wanted the fifth root, n would be 5. And what would I do? I would take 2 pi, 4 pi, 6 pi, 8 pi, 10 pi, all the way up to the number 5. So that's how I would do it. So that's why when we go back to looking at the roots of, say, the third roots of 1, if this is 1 here, 1 plus naught I can draw a circle always. And if I want third roots, I'm going to split it in 3. 1, 2, 3. If I wanted eighth roots, or something like that, of the number, what are the 8 roots of 1 plus naught I? We just draw the circle again. If I want the 8th roots, I just divide the circle in 8. Plus all the other ones. This, I think, is pi over 4, 45 degrees. And you imagine if I did that, multiplied it by itself 8 times, 1, 2, 3, 4, 5, 6, 7, I'd be back. If I took the second one and multiplied it by 8, I'd go around twice. But I'd still end up back here. And I can find out what that value is. That would be only about, what, root 2 out, I think, or something like that. Or 1, sorry, it wouldn't be root 2. If that's 1, that would have to be less than that. They'd be the same as that. 1 over root 2, I think it's called. Yeah, 1 over root 2. So this point here of 1 over root 2 plus I 1 over root 2 is the complex number when multiplied by itself 8 times gives you 1 plus naught I. So it's one of the 8 roots of 1. So that's what the Moivre did. The Moivre spotted that really handy. You can actually get the multiple, you can get the roots or the square roots or the 5th roots or the nth roots by just using this angle trick. So what are the square roots of 1 plus naught I? They're there and minus 1 plus naught I. Because minus 1 plus naught I by minus 1 plus naught I, when you square it, minus by minus is plus. They give you a naught, that gives you a naught, that gives you a naught, 1 plus naught I. So in other words, this angle here, 180, if you multiply it by itself, you're back. What are the 4th roots of 1 plus naught I? Well, here's one of them. So that's the pi over 2. So that one there is a root. So do that 4 times. So 1, 2, 3, 4. And again, naught plus I by naught plus I, naught by naught, etc. gives you, I think, I squared would be minus 1. So minus 1 plus naught I. And then if you square that, you end up with the 1 plus naught. So that's the way it works. And these are the cubic roots. So again, they're 3 apart, or 2 pi over 3 apart. And there's, multiply that by itself 3 times, that by itself 3 times, you end up here. Another way of writing that is cos 2 pi over 3, cos 4 pi over 3, and 6 pi over 3. So again, we're using exactly the same formula that Moivre used in all that thinking. You just decide, you use the cos 2n pi. So it's cos 2n pi over 3. So when n is 1, it's 2 pi over 3. When n is 2, it's 4 pi over 3. And when n is 3, it's 6 pi over 3. And there are your answers. So use the Moivre's theorem to show that cos 2 theta is equal to cos squared theta minus sine squared theta. And that this is equal to this. Well, these are formulae that are in your tables, they're in the logbooks, and you can look them up and they're there, but you're asked to prove it or show that. Well, really, you have to use the Moivre's theorem here. There's a 2 here, so it looks, and a theta. So they're looking at something like, or cos theta plus I sine theta is your standard complex number. But they're interested in that being squared. So let's look at this. All squared. But what de Moivre said, that was the same as r squared cos 2 theta plus I sine 2 theta. The trick was you could take that 2 down into it. So I now can see that if I were to leave the r squared out of it, that cos theta plus I sine theta squared is equal to cos 2 theta plus I sine 2 theta. Now I'm not finished. So that's what's going on there. I'm going to expand this using the FOIL method, first, outside, inside, last. So that's multiplying it out, and here's the terms. Cos by cos is cos squared, cos by sine is cos sine, cos by minus, there are two of those, and then the I by the I gives us I squared and all that. So we end up here with cos squared, bringing it all together, cos squared theta minus I sine squared theta plus 2I cos theta plus I sine theta. You can see that this is real and this is imaginary. This is real and this is imaginary, because these have an I before it and these don't. So if you're going to equate them with each other, the real parts must equal and the imaginary parts must equal. So if the real parts must equal, cos 2 theta must equal this and sine 2 theta must equal that. And that is what you were asked to prove. Okay, prove that. Expanding the results, bringing the real with the real, we get sine theta is this and cos theta is that. Okay, so more or less that's it. That's the end of complex numbers in terms of the things we've got to do. But we're going to look at, say, some of the questions that they give you. So I'm going to show some of the examples I've given before, take some recent examples as well, and then we might be finished before 3:30. So how can they make complex numbers into an interesting question? Well, the one thing about your course, when they changed the syllabus in 2015, they made it so that there were no choices on the paper. Every question, there used to be choices before, the syllabus was slightly larger, but people could leave bits out. But now they said, no, we're going to keep all the bits together, and if they're all together, then we can ask any bit in any question and link any part of the course to any other part of the question, because they didn't leave any bits out. Okay, so let's look at how they might use different things into complex numbers. How can they integrate them? The first one was arithmetic and algebraic equations. Now, you probably remember BOMDAS and what comes first, or Americans call it PEMDAS, but brackets, order, multiplication, division. But here's an exam question. Well, part of an exam question. Simplify 3 plus I, 3 by 2I plus I squared. So simplify that. So take a minute there and see, just expand that into just real numbers and imaginary. BOMDAS says that we should do certain things before we do other things. So if we look at the brackets here, we can see that there's a thing called I squared, or a power in the brackets. So we're going to do that first. So 3 plus I, 3 by 2I plus I squared is minus 1. Then we say, okay, what's next? We're still inside the brackets and there's a multiplication. So we'll do that first. 3 by 2I is 6I plus I minus 1. Now within the brackets we have two parts. We've got a real part and imaginary. So I'm going to join those up together. The I and the 6I become 7I minus 1. Now I've got the I into that. So I'm going to go 3 plus I by 7I is 7I squared, and I by minus 1 is minus I. I squared is a power, so I'm going to simplify that. So that becomes 3 minus 7 minus I. 3 minus 7 is minus 4 minus I. And that's the simplification of that expression. So that's what's on your course. That's one way they could say simplify. I mentioned earlier that if complex numbers are to be the same, if A plus BI must equal C plus DI, the only way that can happen is if the A values are the same and the A and C values are the same and B and D are the same. So if you've got 4 apples and 3 oranges, The only way you can make that equal is to have another 4 apples and 3 oranges. You can't swap the oranges for apples. So the 2 real parts must be the same and the 2 imaginary parts are the same. So let's see how that can come up as a question. You're asked in the exam to solve s plus ti is to 1 plus 3i squared. And you say, I didn't see that before. That's strange. What's going on? S plus ti is 1 plus 3i squared. Haven't a clue. But I'm going to just multiply this because I might get some marks for that. So 1 plus 3i squared is 1 plus 3i by 1 plus 3i. So we're going to use the FOIL method. 1 by 1 is 1. 1 by 3i is 3i. 3i by 1 is 3i. And 3i by 3i is 9, I squared with the plus. Now, the I squared is really minus. So 1 plus 3i plus 3i minus 9. I look for the real parts. This is real and this is real. So 1 minus 9 is minus 8. And these are 2 imaginaries plus 6i. So I now have that s plus ti equals minus 8 plus 6i. Solve for s and t. Well, if I'm solving for s and t, if s is real and t is the imaginary bit, well, the reals must equal the reals. So s must equal minus 8, the real parts, and the t must equal the 6. And that's all that was going on in that question, even though when you looked at it first, it looked a bit tricky. Now, let's look at this question. kw plus w bar is 20, solve. Now this is where it's really important in any part of the maths that if they use a special symbol that you know what it's for. And the w bar was the complex conjugate. So they're saying that w is equal to 2 plus 5i. W bar, or its twin, must be 2 minus 5i. You're asked to calculate k w plus w bar. So w is 2 plus 5i, w bar is 2 minus 5i. Adding the two together, you get 4 plus 0i. And that's not surprising because if you add the complex conjugate, you should get a real number, 4. So k times this is k times 4. K times 4 is 20, or 4k is 20. 4k is 20, k is 5. So again, it looked trickier than it was. How else can they make this complex number question, integrate with other parts of the course? How can they do it? Well, here's a longer question. X into 1 plus 3i plus y into 2 minus I is equal to 2 plus 3i, or sorry, plus all of that, equals 7 plus 4i. Well, there's a lot going on here. So again, we look at it and say, which of these are real? Like the 7 is real and the 2 would be real. And which of these are imaginaries? Anything with the i's would be imaginaries. So let's just split the real parts apart. That's x, that's 2y, plus 2 is 7. Or if we wanted to put the 2 on the other side, we'd say x plus 2y is 5. Using the I part, we could say, well, 3xi minus yi plus 3i is 4i. And we could delete all the i's now because we can divide by I. 3x minus y plus 3 is 4. And I could take the 3 to the other side. 3x minus y is 1. You've seen these before. These are two simultaneous equations. They're two algebraic equations which you could then solve for x and y. So you can see how they can convert a complex number question into two simultaneous equations. So what else is there? Not much more before we do recent exam questions. Here's the roots of polynomials. We started earlier with, say, an ordinary quadratic equation, something like this, where the x value came down and it cut the x-axis in two places. There are some other functions that just skim it. And then there are others that if you take the roots of them, you'll find that the roots are complex. So x squared minus 6x plus 12 doesn't have any real roots. So let's just look at it from a complex number point of view. Z squared minus 6z plus 12. Find the roots of the quadratic function this. We can use the same equation, the minus b plus or minus, that we always used. We just say the coefficient of the first bit is a, the coefficient of the next bit is b, and the coefficient is c. So in this case we'd say a is 1, b is minus 6, and c is 12. And we could use the formula as before. But when we do, and we do all the sums, we'll find that we're left with plus or minus the square root of a negative number. And the square root of minus 12 is actually the square root of 12 by the square root of minus 1. And the square root of minus 1 is I. The square root of 12 is also the square root of 4 by the square root of 3. And the square root of 4 is 2, so it's 2 root 3. But really what's happening here in this, we're showing that if you've got a quadratic equation and the quadratic equation is in Z, and you find it, you're most likely to find that the square roots will be minus. So therefore you'll have the I value. So I'll just briefly explain what's on these pages without going through line by line of the you can look at the notes later, but let's look at the big picture for the moment. We're saying that if you've got this equation here, what are the roots? So let's just go back for a moment to a parallel in real numbers. Let's imagine that f of x in real numbers was this. And it says, prove that x equals 4 is a root. What you would do is you'd say, when x is 4, plug it in. What's f of 4? And you'd say, 4 squared is 16, minus 8 is 0. And you'd say, that's great. 16 minus 8 is 0. That's a root. X minus 4 is a factor. What's happening in complex numbers just looks a bit more complicated, but there's not much more going on. F of z here is z squared minus 6z plus 12. And it says, show that z plus root 3i is a root. So show that that's a root. Show that the answers obtained are roots of the equations. So really what they're saying, z equals 3 plus root 3i. If you want to prove that that's a root, everywhere you see z, just like everywhere you see x, you've got to put in this. So you say 3 plus root 3i squared minus 6 times 3 plus root 3i plus 12. And you do that, and you multiply them all out, and you go through the calculations, and you'll find that it's 0 plus 0i. So line by line by line, you go through these. You can do it out slowly yourself, but you can see that 3 plus root 3i, well, that'll be 3 by 3 is 9, and that by that twice, plus the 3i squared. And you can calculate the whole thing out. But that's how you find a root. Okay? If the two roots are 3 plus, if one of the roots, by the way, is 3 plus root 3i, the other one will always be there. The complex conjugate will always be there. So you could prove that as well. You could go back into this one and say put in 3 minus root 3i squared minus 6 times 3 minus root 3i plus 12. And that would also turn out to be that. So the two factors are, now remember, if x equals 4 is a root, x minus 4 is a factor. So if this is a root, z minus 3 minus root 3i equals 0 is a factor. It's so much longer than this. We're so used to that being so tight, but this is much longer. Really, there's just one more thing in it. But it's 3 minus 3i instead of just 4. So if that's a root, that's a factor. So if you're told that this is a root of a complex number, you're also told that that's a root, because by definition it has to be in there. So if that's a root and that's a root, these two must be factors. So if those two are factors, remember back in the land of real numbers here, I think the other factor was x equals minus 2 or something. Then we would say x minus 4 by x plus 2 were the two factors. We can multiply them out and get something in terms of x squareds minus 2x minus 8 or something like that. What we're doing here is we're saying, well, if that's one root, or sorry, if that's a factor, this must be the other factor. And that by that, z minus 3 minus root 3i by z minus 3 plus root 3i must also be the equation if it's a square. So we can multiply z minus 3 minus 3i by z minus 3 plus 3i, and we're back to the original. Now, some people are used to using this technique, and they say if one of the factors is 3 plus 3i and the other is 3 minus 3i, then the number in the middle, I think, is the sum of the roots. So that plus that is 6 because they cancel. And the product of the roots turns out to be, I think, 12 if you multiply those across. So that's a trick some people use. You don't have to know it. But f of z is z squared minus the sum of the roots by z and the product of the roots. The sum of the roots is 6. The product of the roots when you multiply them together is 12. And again, you get the same equation. So this is the, I think this is nearly the last, but we're saying given that z1 is equal to 1 plus 3i is a root of the equation this, find the other two roots. So this is a cubic equation. Now, not necessarily likely, but it can be asked. Find the other two roots. Well, we did this for, I think we did this beforehand. I think we had a cubic expression or something like that. And somebody said it went through this point here. I think the point was 2 or something like that. So let's say that's a cubic expression. So many x cubed plus so many x squared plus so many x plus whatever, 17 or whatever. And let's say this point is on it. Well, if that point is on it, well then x equals 2 is a root. Therefore, x minus 2 is a factor. Then x minus 2 goes into this. So let's look at it from a complex number point of view. Given that that is a root of a cubic, find the other two roots. Well, okay. There's a few ways of doing this. If z1 equals 1 plus 3i, there must be another root, which is z1 bar, which is 1 minus 3i. So both of those must be roots. Therefore, z1 minus 1 minus 3i and z1 minus 1 plus 3i must be factors. So what's going to happen here is we're going to multiply z1 and that to get the other factors. All the way up, I'll end up with a z squared thing here. Z squared thing here, I've got the square, the quadratic, and I know that the quadratic has to go into the cubic. So the z squared has to go into the z cubed. How do I do that? Well, I can get the z squared into the z cubed. How many times does z squared go into z cubed? Z, how many, etc. And I end up here with Z squared into Z cubed goes Z. So Z by Z squared is Z cubed. Z by minus is minus 2Z squared. Work all that out. I take the lines down. How often does Z go into minus Z squared? So, okay, so I'm dividing that into that. I get this. I've this much left over. Okay, how often does Z go into Z squared? Z squared minus 2Z. Okay, so let's just take that. Apologies. I'm dividing the quadratic, which is the second one I got, into the original cubic. So Z squared into Z cubed goes into Z times. Z cubed minus 2Z squared plus 10Z. I take one from the other. The 2 from the 3, that becomes a plus, that becomes a minus, etc. I'm now left with minus Z squared plus 2Z minus 10. How often does Z squared go into minus Z squared? Minus 1. So I do that. Minus 1 by that is this. Minus 1 by minus 2 is plus. Minus by 10 is 10. So I end up with nothing here. So the third root is Z minus 1 is naught. Or Z equals 1. Or 1 plus naught I. So the third root is 1. So that's as tough as it can get. Don't expect a cubic, but it can happen. They could have said that another way of doing that question was they could have given you the cubic expression at the start, and they could have said the cubic expression is Z cubed minus 3Z squared plus 12Z minus 10. And they're saying Z equals 1 is a root. You'd say, okay, well, if it is, Z minus 1 must be a factor. If Z minus 1 is a factor, I should be able to divide in. Z minus into Z cubed would give me Z squared. That would be Z cubed minus Z squared. Then I could say they cancel. Minus Z squared plus 12Z. I say how often that's that go in? Minus Z minus Z squared plus Z, or whatever, and then I get that. They cancel. Was it 10? Might have been 10. Let's assume I should have got the right answer there. Hopefully, basically you divide. I'll check that, but really we should be. I think that's okay. Apologies. I should have got the root up there. So that would be the quadratic I get from the dividing the one into the other. Now, okay, so let's look at some recent exam questions on complex numbers and where they are. Okay, I'm going to look at the 2020 question, and we're going to look at just how straightforward they are in a way. Find two complex numbers that satisfy the following simultaneous equations. IZ1 is equal to minus 4 plus 3i, and 3Z1 minus Z2 is 11 plus 17i. IZ1 is minus that, and 3Z1 minus Z2 is that. So give that a try for a minute. Now, what you do going into the exam is you say, I've done all the complex numbers. There's only addition, subtraction, multiplication, etc. So it's got to be one of those. So the first one is IZ1 is equal to minus 4 plus 3i. And I'm interested in this. I don't like the I. I don't like the I on this. I'm going to divide by I on both sides. That will cancel that. I don't like, so I'm now finding that Z1 is equal to minus 4 plus 3i over I. Not really a lover of I on the bottom either. That's a complex number, so I'm going to use its complex conjugate. So what one is that? Well, that should be minus I and minus I in that sense. Or I could use, well, in this, yeah. And I'm going to multiply that by that. So I'm going to multiply the 4 by the minus, so that should give us 4i, I think, because the two minuses should cancel. The 3i by I should give me 3i squared, but there's a minus, and the I squared is minus anyway, so I think that's going to be 3 plus 4i on the top. On the bottom, I by I would be I squared, would be minus 1, but with a minus, it would be just 1. So Z1 is equal to 3 plus 4i. So that's the first answer. The second one is an equation that says, given that I know what Z1 is, 3 times Z1 minus Z2 is equal to 11 plus 17i. But I already know what this is. So 3, I think it's 3 plus 4i. Minus Z2 is this. And no different to any other equation. I don't like Z2 on this side of the line. I'm going to move it to the other side. I'm going to keep the rest on this side. But I'm going to move the minus 11, minus 17i. And I should be able to join up the reals and the imaginaries and solve it that way. And that's that. So that's one question. The complex number 3 plus 2i and 5 minus I are the first two terms of a geometric sequence. Now, a geometric sequence, they're linking that to the geometric sequence was something like 2, 4, 8, 16. Shra Ulriach, a geometric series or sequence. So what we're saying is that if this is the first one, T1, and this is T2, T1 by something is T2. And they're saying find the ratio. In other words, find R. What by the first one gives you the second one? Well, if T1 by R gives you T2, R would be T2 over T1. Or really what they're saying is the ratio is the second number divided by the first number. Complex numbers, division, how do you do it? Well, you know how to do division. You just bring in the complex conjugate on the top and on the bottom, and you solve it. Now, this is a nice part of the question. It says, use the Moivre's theorem to find T9, the ninth term of the sequence. Write your answer in the form A plus BI. So let's imagine that you found R is equal to something. You found the answer. Let's say it's 1 plus I or something like that. But you want T9. T9 is equal to T1 by R to the power of 8. So you want T9 is equal to the original number, 3 plus 2i, by 1 plus I to the power of 8. Now, you're not going to spend your time doing that to the power of 8 because it would take you too long to multiply them all out. So you're going to use the Moivre's theorem. So let's imagine that it was 1 plus 1. You say you go out 1 and up 1. 1 plus I. If that's 1 and this is 1, this must be the square root of 2. Because 1 squared plus 1 squared is that squared. So we now know the length of that. So rather than writing that as 1 plus I, you're saying it's the square root of 2 by this angle here. Now, it happens to be 45 degrees, but we could work out what the angles were because it's the inverse tan B over A. So it's 1 over 1. So it turns out to be pi over 4, 45 degrees. So 1 plus 1 is really the square root of 2 cos 4 over pi over 4 plus I sine pi over 4. How do you find the 8th power of that? 1 plus I to the power of 8 is root 2 cos pi over 4 plus I sine pi over 4 to the power of 8. We can take this part and say root 2 to the power of 8 times cos pi over 4 plus I sine pi over 4 to the power of 8. And with the Moivre, we can take it down and multiply the 8 in there. So it's root 2 to the power of 8 cos 8 pi over 4 will be 2 pi plus I sine 2 pi. And root 2 to the power of 8 is, well, whatever, it's root 2 squared would be 2. Root 2 to the 4 would be 2 by 2 would be 4, and root 2 to the 8 would be 8. Or maybe, yeah, we could work it out on the calculator. Okay, so that's fine to be sure. So that's that question. And the final question then is 3 plus 2i is a root of this. So 3 plus 2i is a root. Find the value. It's z squared plus pz plus q. So if it's a root, you plug in 3 plus 2i into it. So 3 plus 2i squared plus p times 3 plus 2i plus q is 0 plus 0i. We work these out and we say that's FOIL method, 9 plus 12i minus 4 or something like that, plus 3p plus 2pi plus q equals 0 plus 0i. And hopefully what we'll find is if we bring all the real parts together, we'll find that the real parts give us an equation 9 minus 4 plus 3p plus q is nothing. And the imaginary parts gives us 12 plus 2p equals nothing. That should solve for p. We should be able to solve for q. V is equal to this in the form this. So really what you're asked here in this question is you're told that V is equal to 2 minus root 3i. Sorry, 2 times root 3i. Write that in polar notation. So what you do is you just go to the x-axis. Sorry, I don't have any square left. But we say 2 minus, so 2 is positive, minus 2 root 3i is down here, 2 minus 2 root 3i, and your job is to find what that value there is. We know that that's 2, we know that that's 2 root 3 in terms of size, we know it's minus, and we then have to work out what that r value is. How do we do that? Pythagoras, we know the length. How do we find the angle? Well, we know that the various tan of this angle, if we come across this angle here, we should be able to know the two sides there, because we have the tan of it. Okay, if we turn it around this way, for example, we would have the two, the opposite and the adjacent. So we should be able to find the angle. We know the angle. We can therefore write this equation as something like r into cos theta plus I sine theta. Use your answer to find two possible values of w where w squared is v. So what they're saying here is that, let's imagine that that's the v you had, and you want to find out what are the two roots of that. So basically we want the square root of v. Well, whatever the length is, let's say that was r, the w, if it's the square root of it, will be the square root of r. So it'll only go out half that, or the square root of that amount. And what will the angles be? Well, you'll probably find that the angles are half the original angle from 0, 0. Okay, or something like that. But we can find the two of them because you can do the square root, and then instead of you'll take 2 pi over and 2n pi, so 2 pi divided by 4 pi divided by, or sorry, divided by a half, etc. And that's how you'll solve the two. So have a look at the solution for that, see how it works out. But basically what we have is you've drawn the graph, you found out where the points are, and then you can take the square root by taking the angles as shown in the Moivre. So sinna will, tá sé Fécraigh nóméid chuna ceathair. Thank you for staying with me, and I look forward to seeing you again at 4 o'clock. So thanks for your time and thanks for the questions coming in. Slán tamil.